Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at differential form of continuity equation. I believe that you have learned about the fundamental laws in the previous part of our fluid mechanics course. And fundamental laws governs three things, which is conservation of mass, conservation of momentum, and conservation of energy. And you have derived the equation which governs these three laws in integral form, which you call continuity equation, momentum equation, and also energy equation. However, those equation was in integral form. But right now, we are going to create this equation again, but this time in differential form. So basically, for continuity equation, which is the equation that we use for conservation of mass, the integral form and the differential form is basically the same equation. It tells about similar things. But these two equations, even though it represents the same thing, but it has different use for different application. So let's take a look at the continuity equation that you have learned before, which is in the integral form. So for integral form of continuity equation that you have learned before, it looks something like this. So this is continuity equation in integral form. And it looks something like this. So 0 equal to d over dt integration of control volume rho dv plus integration of control surface rho v dot n dA. And basically this equation tells you that in a control volume, the change of mass flow rate inside that control volume plus the mass that goes into and exit of the control volume through the control surface, the summation of that is equal to 0, which means that if you have the flow that goes into the control volume minus the flow that goes out of the control volume plus whatever changes inside that control volume, everything is going to equal to 0. And if you have steady flow, so basically this term becomes 0 and you are left with mass flow goes into the control volume minus the flow goes out of the control volume equal to 0. So this is m dot in minus m dot out equal to 0. This is for steady flow. And this term becomes rho 1 v1 a1 minus rho 2 v2 a2 equal to 0. Okay, and we know that from this equation that if the flow is steady, the mass flow rate m dot is equal to rho times velocity times area. This is a very important equation because we are going to use this a lot when we derive the continuity equation in differential form. Okay, so now let's take a look at the continuity equation in differential form, which is the topic for this video, right? So continuity equation in differential form. Okay, so first of all, we must know the difference between integral and differential. The integral form represents the quantity of the mass flow as a whole volume. For example, if you have a control volume that consists of machines such as turbine, and if we draw the control volume around that turbine, then we are going to use the integral form. But differential form represents a control volume that is very small. We are just going to take an element inside that machine, for example, inside that turbine, and we analyze that small element and see what are the mass that goes into and exit of that particular element. I will show you in an example later how we can use this differential form in order to solve a problem related to fluid mechanics. But first of all, let's derive the continuity equation in this form. From the fundamental laws, we clearly know that the mass that goes into the control volume minus the mass that goes out of the control volume is equal to the rate of change of mass inside that volume. And as we said before, if the rate of change of mass inside this volume is 0, the flow is called steady flow, so mass flow in equal to mass flow out. So let's write that equation first. So mass flow in minus mass flow out equal to the rate of change of mass inside that volume. And because our volume in differential form is very small, we're going to call it an element. Okay, so this is m element. And now let's draw that particular element. And I'm going to use blue here. So let's say that this is your element. And this element is in X and Y coordinates. So this is X and this is Y. This box or this element is a 2D element out of a 3D box. Okay, so let's say that this is that box. That is that 3D box, and we are going to make it 2D. And I'm going to label the length here as dx. And I'm going to label the length here as dy. Okay, so dx is basically here and dy is basically here, which means the depth of this 3D volume is dz. And remember that this is very important for our derivation later. And now what I have is basically the flow that goes into this control volume and the flow that goes out of the control volume. And that is in X direction, but I also have the flow that goes into the control volume in Y direction, and there's a flow that goes out of the control volume in Y direction. Now let's label this flow that goes into and exit of the control volume. First of all, we know that m dot is equal to rho times velocity times area. So that is what we are going to use. So the flow that goes into the control volume in X direction, I'm going to label it rho times velocity times area. And area at this side is actually dy times dz. Am I correct? Does that make sense? So dy dz is actually here. Okay, it's the area that is normal to the direction of the flow that goes into the control volume. And similarly, in y direction, the flow that goes into the control volume is rho times v times dx dz. Okay, and dx dz is actually this area. And if you notice here, what I did is rho is rho, and then velocity is u in x direction, v in y direction. Okay, and this is of course the area. This is the area. This is the density. Okay, so velocity in x direction is u. Velocity in y direction is v. And later, you're going to see that velocity in z direction, we're going to label it as w. So now, the flow that goes out of the control volume in x direction is still rho u, but because the flow has traveled along this distance, which is dx, it has traveled in x direction, we're going to assume that rho u is going to change its value a little bit. And we're going to represent the change as plus del rho u over del x times dx. And now you have the velocity times u times the area, which is dy dz. Okay, and if you notice, these are similar terms. Okay, the area is still similar. The difference is just this part. Now, let me explain to you why we come up with this term. Right? How can we come up with this term? Right? So don't worry. Let me show you how. So now let's say that you have a graph that looks something like this. Right? In x-axis you have x, and in y-axis you have rho times u. And rho times u change across x. Right? And you are here. Okay? So this is your rho u at point 1. And now, when you move across x, let's say here, okay, you have moved across x, and this is now your rho u2. Now, my question to you is, what is rho u2? Okay, your rho u2 now is rho u2, let me write it here, rho u2 now equal to, okay, it must be rho u at point 1 plus whatever the slope is here times the distance x here. Okay, so the slope here is del rho u over del x, isn't it? So this has to be plus del rho u over del x times the distance here. That's how you get to rho u2. So this is going to be multiplied by, let's say this is dx. So this is multiplied by dx. Okay, so that's how you obtain the small change in rho u. And this term is exactly similar with this term, right? And let me demonstrate to you again in y direction. Okay, so for y direction, let's label it. So this is going to be rho times velocity in y direction, that is a small letter v, plus the change in rho v in y direction. So that will be del over del y. Now this is rho v times the length, which is dy. This is inside the big bracket times the area. This is dx times dz. So these are all basically the mass flow rate term, right? And mass flow rate, as we know earlier, is m dot equal to rho times velocity times a. We are just adjusting the terms of velocity and area depending on our new element here. Now what you have is basically m dot in minus m dot out. So if I color code this, let's say that m dot in is green, okay? So this is your m dot in and this is your m dot in, right? And let's say that m dot out is blue, okay? So this is your m dot out. So this is, everything is m dot out, and this is also m dot out in y direction. Later we will combine these terms together and form the equation that we are looking for. But finally, we have one more term that we have not touched yet, which is the change of mass inside that element. And for that final term, I believe that everybody knows that mass is equal to rho times volume. Okay, so let's take a look here. I'm going to copy this element. So this is d over dt of the element is equal to d over dt, and mass is actually rho times volume. Okay, but volume is now dx times dy times dz. Can you see that? So this is equal to rho times dx dy dz. Okay, and I'm going to put it here. So rho dx dy dz. And finally, we have all the terms that we need. And now this term is actually here. Okay, now it's time to combine everything to form a long equation that later we can simplify and form the differential continuity equation. Now let's do that. Okay, right. So let's start with the m dot in. So our m dot in is rho u dy dz and rho v dx dz. Now rho u dy dz plus rho v dx dz. Okay, so these two are done. Okay, now the flow rate that goes out, we must use negative sign. So for m dot out, we have these two terms which is quite lengthy, right? So let's start with this term first. Okay, so this will be minus rho u plus del rho u over del x dx times dy dz, and then minus this term. Okay, so that will be rho v plus del rho v over del y times dy dx dz. Okay, so we have everything. We have m dot in minus m dot out, and then equal to this guy here. Okay, so this is d over dt times rho dx dy dz. Now I think immediately we can see a few terms that we can cancel out. Okay, let me show you. So basically this term rho u dy dz will cancel out with this one, because when you take this out of the bracket, then it will be rho u dy dz also, which means that you can also remove this equation because it will cancel out with this one. So in the end, you are left with these terms. Okay, now let's write it. So this will be del rho u over del x times dx times dy times dz. There's a minus sign in front, minus del rho v over del y times dy dx dz equal to del over del t rho dx dy dz. And again, immediately you can cancel out these three terms. Okay? And you'll end up with del rho over del t is equal to minus del rho u over del x minus del rho v minus del y. Does that make sense now? We know that we only use two dimensions to come up with this equation. But imagine what happens to this equation if we have three dimensions, which is x, y, and z. So you will ultimately have u, v, and w as the velocity component. So I'm going to add the z dimension. So add z dimension. So you will have del rho over del t, I'm going to put minus here, equal to del rho u over del x plus del rho v over del y plus del rho w over del z. Okay, so now basically you have all three dimensions inside this equation, but it is still a little bit too complicated to solve. So let's see how we can reduce it further. And if you notice here, we have here a dot product, isn't it? Okay, integration of a dot product. So we can actually separate them further. Now let's write minus del rho over del t here. So this is equal to rho del u over del x plus u del rho over del x plus rho del v over del y plus v del rho over del y plus rho del w over del z plus w del rho over del z. We're just expanding the differentiation of the dot product. Next, I'm going to arrange the row term together. So these row terms, and this equation becomes, and if I move everything to one side and equal everything to 0, so this becomes del rho over del t plus u del rho over del x plus v del rho over del y plus w del rho over del z plus rho, and group everything together. This is del u over del x plus del v over del y plus del w over del z equal to 0. Now you may think that this equation might be getting too long and it becomes even more complicated. We were just trying to reduce it and simplify it so we can use it later. But I assure you that this is the process of simplifying the equation. Okay? And if you notice here, these terms is called the substantial derivative. Okay? Substantial derivative. Or sometimes we also call it material derivative. Okay, so substantial or material derivative happens when you have this del over del t plus u del over del x plus v del over del y plus w del over del z. And it could be any variables, any scalar variable. So this could be phi. Okay, but in our case, this is rho. And material derivative can be simplified in terms of writing by using capital D. So this is actually d over dt. Okay, and let's say this is still phi. Right, and we know that our phi in this case is actually rho, which is density. Okay, so this is our variable, which is density. Right, so what happens to this term? So everything here will become d rho over dt with the capital D, which means that this will become plus rho, just this term, del u over del x plus del v over del y plus del w over del z, and this is equal to 0. And this is actually the equation that we are looking for. Okay, this is the most general form of continuity equation in differential form. Okay, so this equation is very important. Of course, we can simplify this further, but this depends on the assumption that we make. For example, if the flow is steady, then the equation becomes even simpler, right? And there is another way to write this equation, which is using del. And the symbol of del is this. Okay, and del is equal to del over del x. Now, this is different del, okay? So, del over del x in x direction plus del over del y in y direction plus del over del z in z direction. So ijk, this is the vector form. Okay, and we can simplify this by writing d rho over dt rho times del dot v equal to 0. And v here is v equal to u in x direction plus v in y direction plus w in z direction. Okay, so now these terms looks very simple and it makes it easy for you to remember in this form. Then if you memorize this form, then you can always use this definition and expand it back to this form. And you can use the definition of this material derivative and go back to this form. And then you can use it to solve your engineering problem. Okay, one more thing. Let's see what happens if the flow is incompressible. If the flow is incompressible, so let's write here for incompressible flow. What happens in incompressible flow is that the density never changes. Okay, so d rho over dt is equal to 0. And you end up with this term only, rho times del dot v equal to 0. Okay, so from this term, we know that the d rho over dt is 0. So you end up with this equation. And if we expand this, so this is rho times del u over del x plus del v over del y plus del w over del z equal to 0. And of course, we know that the density doesn't change, but it is not 0, which means that this term is the one that is actually 0. So, the summation of del u over del x plus del v over del y plus del w over del z is equal to 0. And we can simplify it by writing del dot v equal to 0. And this will be the final form of your differential continuity equation when you assume that the flow is incompressible. Okay, so what I need you to do now is to go over your notes and repeat this process again, starting from this box. Okay? Draw this element and then label the length dx and dy and then come up with this equation. Okay? The flow that is going into and exit of the control volume. And then combine those equations and then reduce it so that you obtain this formula. And you do this again and again until this becomes second nature. If you do this multiple times, then I promise you, next time you will be able to do it even without looking at your notes. So that's all from me for now, and I'll talk to you soon. Bye!